once again. Thank you, committee, for inviting me, and thank you for coming. I would like to introduce you to the work we do in our lab with mushrooms, and I would like to describe a study we did recently where we got quite contradictory results, but we still managed to publish them anyway. So I want to show you that even if you get results you don't really like, you don't have to be afraid to publish them if you frame them in a certain way. So in our lab we work with mushrooms. I like to say mushrooms because when I say fungi, many people will usually associate that with yeast or molds, and that's not what we do. We work with actual mushrooms from the forest. So mushrooms are well known for being excellent heavy metal accumulators. They can accumulate over 1 gram of a metal like silver or zinc or cadmium per 1 kilo of dry weight. You might think it's not that much, but it's actually a lot in the kingdom of fungi. So scientists have thought, well, maybe we can use this propensity to accumulate the metals in some useful way. So how about biosensors? We can collect the mushrooms in the forest, measure how much metal they have, and then say like, ooh, this site was polluted. Unfortunately, the mushrooms accumulate the metals both on pristine and polluted sites, so we can't really use them as biosensors. So then we thought, okay, if they accumulate so much heavy metals, and this is actually a question I get asked quite often, can we use them for some sort of biomining? Well, it's not that much metal they are accumulating, and also they are really hard to work with, they are hard to propagate in the lab, they are hard to collect, they are very dependent on water, etc. So not very good for biomining either. Then we thought, okay, because most of these accumulating mushrooms, they are ectomycorrhizal, so they grow in symbiosis with plants. So maybe we can use them to help plants grow at polluted sites for the purposes of phytostabilization and phytoremediation. Maybe we can actually do that. There are studies and there are groups dealing with this topic, and it has been shown that the partnership between the plant and the fungus is quite delicate. Some plants grow only with some mushrooms, and other mushrooms are quite promiscuous and will grow with any plants. But you never know beforehand, and also you can't generalize if the relationship will actually get more metal from the surroundings, or if the mycelium will block away the metal from the plant. And it really depends on what application you want to use this symbiosis on. So not really that reliable. But then we thought, maybe we can use only the heavy metal related genes to create custom GMO plants to use and then use those for phytostabilization or phytoremediation. So we got into studying of these genes, and we have already identified plenty of transporters and binding peptides and methylthionates. But when we try to do the transfer from the mushroom to the plant of a gene, which my colleague did, he's not here today, but the results there were not very convincing, and it's quite difficult to work with plants in the lab. So then we thought like, okay, maybe we can only work with the mushrooms because we actually work with mushrooms. So let's try to do a GMO mushroom and see how that goes. Now, briefly about what we do with the mushrooms when they come to our lab. We get the mushrooms from the forest, and we smash them in kind of toothpaste-like consistency and centrifuge them, and then the liquid is subjected to gel chromatography, the size exclusion column. And we use columns that have a cutoff limit at about 13 kilodaltons, because we are mostly interested in smaller proteins or peptides that bind the metals. And in this case, we were interested in how does the metal accumulation profile look in Russula brezadole, which is a zinc accumulator, and how does it look in Hebeloma mesophyllum, which is a kind of all-over accumulator. It accumulates silver, cadmium, zinc, but not in that very high amounts. And what we got to know was that in Rusula Brezadole, the accumulation profile, we do the accumulation profile such that when you do the gel chromatography, you collect fractions one by one, and then you measure metal contents in each fractions. So down here, these are numbers of fractions, and here is metal content. So you can see for the Rusula, the profile looks something like this, while for the Hebeloma, the profile looks like this. For a lack of better wording, I have called them X-wing and TIE fighter profiles. And this was on the protein biochemical level. And then we got to study the genes that are responsible for producing this protein in more detail. And we got to know that it was something we call zinc-binding peptide. And then we tried to take this zinc-binding peptide, gene for it, and transform it to the Hebeloma mesophilum and try to change the TIE fighter profile into the X-wing profile. That was the idea. And my colleague Vojta Beneš did this experiment where he actually transformed the mycelia of the Hebeloma with the gene from the Rusula, and the results were really great. You see, the wild-type mycelium, it doesn't really grow on high levels of zinc, while the GMO mycelium, it still grows quite nicely. So we were really happy with this result. But in biology, you can't always rely on only one type of study. So of course, we wanted to know if actually the accumulation profile changed as well. So we took a little bit of this mycelium, put it on the on the GPC column, and measured zinc contents in each fraction. And what we got was this. It was the original profile, still the TIE fighter curve, not the X-wing curve that we wanted. No gene here, although expression was there. So it was quite disappointing, and we didn't really know how to put these data together and how to publish it. Like, why did it work in one experiment quite nicely, and the other experiment didn't show any change at all? So, what to do when you have results like this? Well, first, choose a journal that is not too picky about your data. So you can't hope to really publish this in a high-impact journal, but you can choose maybe a journal that is an institutional journal. If your methods are right, you can choose a journal that is paid but still has a peer review, etc. And then think what other experiments you can do. So we did another experiment with the protein ex vivo just to try the binding capacity of it, and that worked very well. So plus data for us. But then we did fluorescence microscopy, and we saw that the insides of the mycelium of the wild type looks completely same as the GMO mycelium. So that was not the way to go. But luckily then we met a guy from the analytical chemistry department, and they have mass spectroscopy there, a machine that we could hook our gel column to and get direct online data. So no collecting fractions, no bringing them to atomic absorption spectroscopy, no waiting 1 or 2 weeks for data, but direct online data on very small amounts of samples, and of course with superior resolution. And when we looked in the middle fraction, in the middle of the diagram, we saw that actually for zinc here, there was a tiny slope when comparing the GMO mycelium to the wild-type mycelium. Similarly, for cadmium, there was also some increase here in the middle section, still not the nice curve as it was with the original organism the gene was from, but still it was something we could use as arguments to conclude that single gene insertion is not enough to change innate biology of zinc flow in Hebelboma mesophyllum. And that's it. Thank you.
And your questions, please. Okay. Do you have some experiments in multidisciplinary approach?
We do, but we decided we would not talk about that.
Okay. Any other questions? About mushrooms and so on.
Okay. So, what is the reason the mushroom accumulates so much? Why did it do that?
There are several theories. Theory number one, it's protection against insects or bacteria, because there is the kind of arms race between organisms. For example, for zinc is one factor necessary for virulence of organisms. So when the mushroom takes zinc from around, it's not accessible for other organisms. Or it could be the other way around, that once upon a time there was a zinc-rich environment and only the mushrooms that could accumulate a lot of zinc and survive in such environment have survived. Or it could be because there is this theory that, because it's really strange actually, because you know mushrooms, of course, they grow the spore carps and in a week or two it's dead again. And a lot of the metal is inside the spore carp, which is deteriorated, and then the metal stays in the soil again. So it's a kind of weird cycle really. So maybe it is to allow only